Hello, everyone. This is not exactly the talk that was on the agenda and not exactly the speaker that was in the agenda. I hope I won't disappoint it. Sorry for that. So our topic today is ZK in a nutshell. This is our plan. We will first talk a bit about why should we talk about this topic in general. Then we will look into some fun math, and then we will help Dora to find ZK in the ZK rollup. So why does ZK definition matter in general? It happened so that in blockchain and in Web3, we started putting ZK into everything. Maybe because it sounds cool, maybe for some other reason, maybe for marketing, maybe for fun, but it became a bit confusing. If we have ZK, what can we do? What can we do with that? Like, what is its unique mathematical property that we can use, and how can we utilize it? So let's go a bit with the history. ZK is pretty ancient. Not as ancient as the Rosetta Stone, but still pretty ancient. The first paper was in almost 35 years ago, more than 35 years ago. And it had nothing to do with blockchain. It was years before Bitcoin and Ethereum and whatever. But the first paper was more than 35 years ago. And we mostly know ZK from ZK rollups. Maybe more advanced people know ZK from Zcash, but most people from ZK rollups. And the first architecture of ZK rollup was described in this ETH research post in 2018. And as you can see from the title, it was like roll up, roll back, snark sidechain. It's no way was a ZK rollup, but for some reason we called it ZK rollup. I don't know the history, but okay, we have to deal with that. So we often say zero knowledge proof. But what proof? We need to differentiate between proof of statement and proof of knowledge. Proof of statement proves that some statement is true. For example, z is a square modular n, meaning that z equals x square mod n. What is x? We don't know anything. We just know that z is a square modular n. Or two graphs g and h are non-isomorphic. What are relations between these graphs except for the fact that they are non-isomorphic? We don't know. On another side, proof of knowledge proves that the person making an assertion has some knowledge about the statement. For example, I know a value x such that z equals x square mod n. Or I know the isomorphism between two graphs, g and h. And it's quite important to differentiate between two of these, proof of statement, proof of knowledge. And we will take a look at an example, and we will take the problem of graph isomorphism. Some fun math. So what is this problem? We say two graphs with label nodes are isomorphic if they are the same up to permutation of the labels. It might sound a bit cryptic. Let's look at this picture from Wikipedia. We have two graphs, G and H. G and H. The fact that they are isomorphic means that there is some function that we can apply on all nodes in graph G, and as a result, we will get a graph H. So each node of graph G maps one-to-one into a node in graph H. So this is graph isomorphism. If there is no such permutation, they are non-isomorphic. That's it. So we want a proof that two graphs are non-isomorphic, and this will be proof of statement. Some brief intuition behind how we can prove it. Assume we have two graphs, G and H, randomly chooses a permutation P, like this function that will map the nodes of one graphs into something. And one randomly chooses one graph G or H and computes a permutation of this graph. If these graphs were isomorphic, if some external party has graph K, that is permutation either of G or H, they can only guess which graph it was. if they were isomorphic. And as the best thing is to guess, the probability of guessing is 1/2. If we repeat these tasks number of times, the probability of guessing will be negligible. So it looks something like that. We have the verifier chooses a random challenge B and some permutation P, all at random. If B is 0, verifier computes K on G. If B is 1, verifier computes K on H, sends K to the prover checks if K is isomorphic to G, based on that computes C, sends to the verifier, that's it. Then, okay, now we have graph isomorphism problem. So the prover wants to prove that they know the isomorphism such that H equals sigma G. This will be a bit trickier, but we will handle it. So the proof intuition. If sigma is an isomorphism between two graphs, it means that H equals sigma G and G equals reverse permutation of H. So let P be a permutation randomly chosen by the prover. The prover uses rho, some small trick rho. Rho equals P multiplied by sigma to the power of minus C, where minus C is assigned by verifier randomly and it is 0 or 1. So depending on if C is 0 or 1, the prover gets either rho equals P or rho equals P multiplied by sigma minus 1. If one applies rho equals P to a graph, they will get the permutation. If one applies rho equals P multiplied by sigma to the minus 1 to a graph, they will get the permuted reverse isomorphism. So we can a bit understand from this picture. If we apply permutation P to G, we will get T. If we apply isomorphism to G, we will get H. If we apply permutation multiplied by inverse isomorphism to H, we will get T. This is how the protocol looks. The prover wants to prove they know the sigma. They choose some random permutation P, computes T on G, sends the T. Verifier returns the challenge. The prover computes rho, sends the rho, and verifier does some checks. That's not exactly the part we are really interested in. We want to know if this proof has zero knowledge. Okay, informally, zero knowledge means that a verifier can't retrieve any additional information from a prover except for the information clear from the proof itself. In the example of graph isomorphism, our second example, proof of knowledge is zero knowledge. Because when the prover sends the verifier T, this is kind of commitment to the random permutation P. It's not permutation in plain text. And when the prover sends to the verifier rho, again, rho is the commitment to the isomorphism. It's not the isomorphism in plain text. And this is exactly why we needed this small trick with rho. However, in our first example about proof of statement, proof of non-isomorphism, it's not zero knowledge. Because when the verifier, as his first step, computes K, it is expected that it will compute K either on H or G. But the verifier can put some arbitrary graph instead of H or G, and as a result of the protocol, the verifier will know if his arbitrary graph is isomorphic to G. Can we convert our proof of graph non-isomorphism into zero knowledge? Yes, we can. But it would become a bit more complex. So we need to add two things. We need that the verifier should provide proof that the graph it sends is isomorphic either to G or H, and that they know the isomorphism. So it will look something like that. And what is interesting here is that as one of the steps, we will have our previous example, proof of graph isomorphism. So I don't know, for me, it always has been a bit non-intuitive that proof of statement is a more complex protocol than proof of knowledge. Okay, now let's jump to ZK rollups. Because we call them ZK rollups and sounds like there should be ZK. 1 minute on how ZK rollups work. The main use of vanilla ZK rollups is to enable scalability. We have one proof posted to L1, proving that a bunch of transactions is valid. So one proof, many transactions. This is scalability. ZK rollup executes transactions off-chain and posts proof that whatever it did off-chain was done correctly. So far, so good. And this is proof of statement, exactly the statement that the state transition was done correctly. So this is approximately how it looks. We had some previous state, we have some given inputs, what has happened in the block, we put them into the rollup, and we get new state. So now we want to do, is the state correct? To generate the proof and verify the proof, the prover needs to know, as like was on this picture, the previous state and the given inputs. But the verifier, to verify the proof, needs the proof itself, new state, previous state, and input values. So let's think a minute about what are these inputs. We have two types of inputs, public and private. Important thing is that even though we call them private, sometimes we call them even secret, they are not really private or secret. Instead, private input means that they are private from the verifier, meaning that they are consumed by prover only, and that's it. And this is done for the sake of efficiency, because all public inputs, we need to submit to L1, meaning we need to pay for that. And we want to make them as small as possible. Public inputs, oh, I forgot something. Yeah, public inputs is mostly all data that needs to be submitted to L1. And it will include new state root and signature, sender, receiver, functions, contract addresses, function arguments, newly deployed contract data. All these things will be published on L1. Meaning that this is a huge amount of information that is available for everyone. So meaning this is obviously not a zero-knowledge proof. This is a proof of statement that does not have zero-knowledge property. Private inputs mostly include all information that was needed by the prover to generate the proof. So just once again, we have public inputs that are consumed by prover and verifier, and we have private inputs that are consumed only by the prover. We have some intermediate values. The verifier is not provided with intermediate values, but they can derive it from the data they have, and we have the verifier's decision. So if a ZK rollup is generating a proof that Alice sent Bob 1 ETH, both the prover and the verifier will be aware of this information. Who sent, to whom sent, how much of what. So no privacy at all. To sum it up, in the case of a ZK rollup, we want to prove the validity of a state transition. It's a proof of statement, and it does not have zero-knowledge property, because all the information is public, and everything that is not provided explicitly can be derived by a verifier. So there is no ZK in ZK rollup. Can we have ZK in ZK rollup? Yes. While the main use of vanilla ZK rollups is to enable scalability, there are also ZK rollups, such as Aztec, that enable scalability and privacy. And it utilizes ZK exactly for the privacy purpose. How it works? Aztec provides privacy by means of client-side proof generation, meaning that whatever we want to be private, we need to process client-side. Client-side on user's device, such as a smartphone or laptop browser. Then the proof is supplied to the mempool, and the verifier, the sequencer verifies the proof that whatever was executed client-side was executed correctly. And when we say processed privately, we mean that transactions are processed privately, and their outputs through some side effects, and those get added to the global state without revealing any information to anyone except for who conducted the transaction. For example, in case of a transfer from Alice to Bob, Alice executes transactions client-side and emits side effects, and Bob receives side effects, but no one else, just Alice and Bob, that's it. So these strawberry guys are client-side proofs. They jump into the mempool. In the mempool, sequencer verifies the client-side proofs and execute public transactions. And then, as a regular rollup, it builds the blocks. Client-side proof in Aztec is a zero-knowledge proof of statement. But the block proof, it will be like in a regular rollup. It's a regular proof. It's not zero-knowledge. So client-side proof is zero-knowledge. Can we just put ZK in the ZK rollup and add privacy? Not really. Why? Because there is no such thing as abstract privacy. Privacy is a property that some system can have. And to ensure that some system, such as a ZK rollup, has privacy, we need to design it in a way to be private. So it's not just about making a snark, ZK snark, but in the case of ZK rollups, it's also about client-side proof generation. So it should be designed to be private from the very beginning. And that's pretty much it. Thank you so much.
Thanks, Lisa. I really enjoyed the talk. Any questions for Lisa or Aztec? I have a quick one. So I'm wondering, are there any native tools on Aztec that people can use to build privacy-preserved applications? For example, how different it is to build DeFi or gaming on a normal ZK rollup compared to on Aztec?
First of all, if we are talking about private applications, I think it's very hard to build private application on transparent network. But when it comes to building on Aztec and about privacy, I think the thing that might be the trickiest one is that Aztec has two different states, for public state and for private state. And people need to grasp this intuition between this difference. And if it is grasped, I think it definitely requires some efforts, but people will be able, because Aztec is designed to build private applications on top of it.
Thank you. By the way, congrats on announcing the testnet recently. Yeah, so anyone else?
I'm not sure.
Okay, I got one there.
Hi. What about sharing your private state? Do you have any ideas or roadmap there?
Yeah, it's a very good question. Currently, while public state is universal for everyone, for private state, every user has its own private state. And potentially, if we want to have shared private state, we can utilize ZK MPC protocols that will allow us to do that. And I think there is a team who's currently working on something like that to make it possible on Aztec.
Thanks.
Great, thank you. Sounds like Aztec will be the privacy engine for Ethereum.
Exactly this, you got it.
Great, thank you, Lisa.